Üdvözlök mindenkit, én Csabai István vagyok, az Akadémia Fizikai Tudományok Osztályának az elnöke, és akkor ez, aki nem tudná, ez egy rendkívüli osztályülés, egy nyílt osztályülés, ahol egyetlen napirendi pontunk van, Mária Lugarónak a székfoglaló előadásának a megtartása. A napirend az, hogy először én röviden szólok pár szót Mária Lugaróról, aztán megtartja az előadását, utána pedig átadjuk az oklevelet, és azzal abszolút le lesz pecsételve, vagy hivatalosan is, akkor az osztálynak levelező tagjára választották. Tehát Mária Lugaro Torinóban, Olaszországban született, és akkor nekem nincsenek pontos adataim, hogy az akadémián hány olyan tagunk van, aki nem Magyarország, vagy nem magyar születésű, de az akadémiának tagja. Az biztos, hogy a fizika osztály közelmúltjában nem volt ilyen, olyan aki pedig női tag, az meg még kevesebb, jó? Úgyhogy akkor ez különleges alkalom, és nagy örömmel üdvözöljük akkor Máriát itt az Akadémia Fizikai Tudományok osztályában. Tehát akkor Olaszországban született, és utána Hollandiában és Ausztráliában több egyéni ösztöndíjat és pályázatot nyert el, és 2014-ben pályázott a Magyar Tudományos Akadémiának egy kiemelt ösztöndíjára, a kollégák nyilván ismerik, a lendület ösztöndíjra, és azzal költözött Magyarországra, és azóta is akkor itt kutat, dolgozik, és akkor ez lehetővé tette számára, hogy akkor egy kutatócsoportot is hozzon létre, ami folyamatosan gyarapszik, meg hát változik, ahogy ugye a diákok jönnek, aztán kitanulják a szakmát és kimennek. Tehát akkor a Csillagászati és Földtudományi Központnak a Konkolytege Csillagászati Intézetének tudományos tanácsadója jelenleg, és 2022 óta az MTA doktora. És a lendületcsoport, ugye ez egy jó alapot biztosított ahhoz, hogy akkor tovább fényesítse ugye a kutatási területét, eredményeket, és akkor erre alapozva, a kutatásokra alapozva elnyert egy, ha úgy vesszük, akkor még nagyobb presztízsű európai nagy pályázatot, nagy díjat, ezt az ERC Consolidator támogatást, és akkor utána pedig, miután az első lendület lejárt, akkor még egy lendület ösztöndíjat is kapott, úgyhogy szerintem ez tényleg így pályázatok tekintetében ez tényleg nagyon sikeres. És akkor ennek köszönhetően részben, ugye, hogy ezeket a nagyon kompetitív pályázatokat elnyertek, az lehetővé tette azt, hogy olyan témákban dolgozzon, amik hát ilyen high risk, high gain, hogy így fejezzem ki magamat, tehát hogy olyan új területek, amik valamilyen szempontból kockázatosak, ugye új területek, amiket fel kell deríteni, viszont nagyon szép sikereket lehet elérni. Maga a tudományos munkásság, hát arról beszélni fog Mária, de ez is olyan szempontból nekem különösen szívemhez közel, hogy multidisciplináris, tehát én mindig szeretem azt, amikor több tudomány ötvöződik össze, és akkor itt kimondottan a nukleáris fizikát, csillagászatot, asztrofizikát, kozmokémiát egyesíti ez a kutatási terület. Noha a nukleáris asztrofizika, meg a kozmokémia is tulajdonképpen ugyanazt a célt tűzi ki, hogy az univerzumnak, meg a naprendszernek az anyagi összetételét minél inkább feltárjuk, megismerjük, más módszerekkel kell hozzá, tehát a fizikusok inkább nem tudom, spektrumokat nézik, a magfizikai elméleteket, a kozmokémiai terület, amiről régen én nem is nagyon tudtam, ők pedig inkább a Földre érkező meteoritokban lévő különböző anyagszemcséknek a kémiai, tehát a neve is mondja, kémiai vizsgálatával dolgozik, és akkor ennek a kettőnek a kombinálásával, tehát a két különböző háttérrel, két különböző területtel olyan eredményeket lehet elérni, amit külön-külön ugye nem lehetne csak egyik vetületét, vagy egyik részét nézzük a dolgoknak, és akkor ilyen meteoritokban felfedezett csillagporszemcséknek a vizsgálataival, meg ugye a nukleáris folyamatokkal való összevetésével, radioaktív magok tulajdonságainak a vizsgálatával olyan eredményeket tudott elérni, amik tulajdonképpen ezt a területet nemzetközi szinten is nagy lépésben előrevitték, Magyarországon pedig hát teljes mértékben úttörő szerepe van Máriának ebben, mert itthon ez a terület így még részeiben sem feltétlenül létezett. És akkor ezekre a kutatásokra alapozva, tehát ugye multidisciplináris, így akkor maga a kutatóhálózat, amit így alkot, az önmagában már széles körül, de akkor nyilván már ennek a kutatói személyiség az külön hozzájárul, hogy ez a széles körű kutatóhálózat, ez nem csak a különböző tudományágak áthidalásához legyen használva, vagy az történjen meg, hanem ez a csoport, ez mint egy ilyen nemzetközi fókuszpontjává is vált ennek a tevékenységnek, ami így a magyar kutatás szempontjából ez külön dicséretes és külön nagyra értékelendő. Tehát itt találkozhatnak ugye nukleáris fizika, csillagászat, asztrofizika, kozmokémia kutatói, kölcsönösen megosztják egymással az egyes területeknek az ismereteit. Itt van nekem egy statisztikám, hogy az utóbb 2015 óta, amióta Mária itt dolgozik, több mint 100 külföldi kutató járt így látogatóban az intézetben, ami tényleg tovább erősítette az intézetnek egyébként is erős nemzetközi beágyazottságát. Utánpótlás képzésben is jeleskedik, sok kiváló hallgatót, posztdoktort, doktoranduszt felügyel, biztosítva nekik ugye a pályakezdésnek a lehetőségét, és korábbi diákjai pedig itthon is és szerte a világban, Belgiumban, USA-ban, Lengyelországban, Svédországban dolgoznak, folytatják a kutatást, és viszik részben akkor így már a magyar kutatói szférának a jó hírét is. Eredményeit több mint 380 cikkben publikálta, közülük vannak olyanok, a Science és Nature, tehát a legtekintélyesebb, legnagyobb presztízsű lapokban jelent meg. Itt nekem egy olyan szám van, de azóta biztos növekedett, hogy több mint 5000, ez nem növekedett, mert több mint 5000-szer idézték, és a fő munkákat egyesével is több mint 300 alkalommal idézték, számos rangos konferencián vett részt, és díjak közül pedig az MTA fizika díját emelném itt ki. Úgyhogy ugye említettem, hogy Olaszországban született, tehát ő valószínűleg legszívesebben olaszul tartaná a beszédet. Én, mint hallható volt, magyarul tartottam a bevezetőt, de akkor abba egyeztünk, hogy angolul fogja tartani az előadást. Úgyhogy Maria, the floor is yours.
Köszönöm szépen a bemutatást, és köszönöm szépen, hogy olyan sokan eljöttek és eljöttetek, a család és barátok is. A előadás angolul lesz, de a diák pedig magyarul. So I will speak in English, but the slides are in Hungarian, so I hope that everybody will be able to understand and follow the talk. So the title is What Are Stars Made Of? But when I started preparing, I decided I should start asking another question. First of all, what is the universe made of? The universe is made of, we don't know. So 95% of the universe is made of dark matter, dark energy. We don't know what they are. We know they exist because we have physical proof that they exist, but we don't know what they are. So atoms are only less than 5% of the universe, and stars are made of atom. I give it away at the beginning, but I will go into more details. So why do we care about atoms? There's so little of them. In the big picture, they almost don't count anything. Well, atoms is also what everything we know is made of. So the earth that we stand on, everything we eat, our body. And I think it would be interesting to discuss that, but I think any alien will be made of atoms. So if we want to understand our place in the universe, and what is our corner of the universe in the big picture, we have to start with the atoms. So what is an atom? I want to remind everyone, just to make sure we start from the same situation, from the same knowledge. An atom is a particle that is one of the basic makeup of all the matters that we know. And this is an example of a carbon atom. So it's made of a nucleus that is made of protons and neutrons, and around the nucleus there are the the electrons. So there are, in the case of the carbon atoms, there are 6 protons and 6 electrons. And as you can see from the picture, the electrons are not anywhere around it. They are located in orbits that are very specific. So only very specific energy can be taken by these electrons. And the important thing is this number of electrons is the atomic number that controls how the atoms react with the rest of the other atoms. And there is a big variety of atoms. Probably everybody has seen the periodic table of the elements. There are 80 stable elements, and they are structured on this table according to the number of the electrons, because this is what controls how they react chemically with the other atoms, which molecules they make, and everything that we know. So, which atoms are things made of? Which of this type of atoms? If we look around us, everything that we stand on, rocks, minerals, they're mostly made of oxygen, silicon, aluminum, iron, magnesium, and calcium. Life is different. Life is made of oxygen, carbon, and hydrogen, but this is life as we know it on Earth. Other type of life could be made of silicon or other elements. This we have no idea. And of course, we sit on the Earth, so we can analyze very well what is the Earth crust made of. And this is a figure that shows as function of the atomic number, so each number is a different element. There's also the elements are shown here. What is the Earth crust made of? We have to normalize so that silicon is equal to 1 million. We don't have the total number. We can only know relative to each other. So the silicon is very high abundance together with all these other elements that make rocks. Of course, that's what the Earth crust is made of. But then there's a lot of other interesting elements present, for example, elements that we use for industry, like lead and tungsten, or like these precious elements and other elements that we use for our development, technology, etc. And out of all these elements, we can make things like jewelry, we can make mobile phones. They take almost 50 elements to make a mobile phone. So we become very good at exploiting all the elements that we have. So this is the Earth. Well, we know, great. Now let's go to the stars. And I will start with the closest star. So let's start with the sun. What is the sun made of? We know that the sun is a big ball of plasma. It's very hot. It's 6,000 degrees at the surface. It's 15 million degrees in the center. And it's this burning plasma that makes a lot of energy that get to us in form of photons. But what kind of atoms make the sun? Is it the same as the Earth? Can we know that, exactly which elements make the sun? Yes, because we can analyze the light that comes from the sun. We can split it according to its color. So this is the sun spectrum. There's many different colors. But you see all these little black dots. This is not a mistake. This is not dirt. This is actually what is telling us the atoms that are at the surface of the sun. And how it works, basically, when you have an atom, like I showed you before, if there's a photon coming from the central part of the sun, it can hit one of the electrons, and the electrons will absorb that photon, catch it, and jump to another energy level. And this is so very specific. Each atom will have different energy levels, so it can only capture given photons' energies. So different energy meaning colors. And that's why some of these photons don't get to us. That's why there's black spots here, because they cannot reach us. They are captured by the atoms at the surface of the sun. And this sounds okay, the process is relatively simple, putting it this way, but when you actually look at the spectra of the sun and trying to interpret it, to actually read how many atoms of carbon are there, how many atoms of magnesium, This is quite messy. It's not a very easy line, let's say. There's a lot of zigzag. We can see dips. So this is as function of the wavelength. So the color of the photon is on the x-axis, and this is how many photons are coming. And you can see these lines that go deep down, because this is where the atoms of iron is capturing the photons. And this is where atom of magnesium, etc. But you would think, okay, maybe we solved this quite a long time ago. No, only 100 years ago, exactly, we discovered what the sun is made of. So it was not easy, and people thought the sun is the same as the earth. It's made of silicon, oxygen and calcium. And instead, thanks to the work of this famous astronomer, Cecilia Payne, that 100 years ago we discovered that the sun is made of hydrogen. And this was quite controversial. People didn't really believe it. Why the sun should be made of hydrogen? Everything we know is made of oxygen and silicon. But she discovered this, and now we know for sure. The sun is made of hydrogen and helium, and not of silicon and oxygen like we are. So now, if we summarize, I will show the same picture as before. This is the Earth crust, and this is the sun. And again, in the sun, we don't know the total number of each atom. We normalize him to hydrogen in this case. And both cases are logarithmic. This means that every marks, here every tick marks, here every second mark is a factor of 10. So the sun is made of hydrogen and helium by 90%. Everything else is at least 1,000 times less. The Earth is almost the opposite. Everything is oxygen, silicon, aluminum, etc. Hydrogen, yes, there's some hydrogen, but it's much less than oxygen. Helium is not even here, because helium is a noble gas. It doesn't go into rocks, so we don't have any on the Earth crust. So this is the picture, and there is one more way that we can check if we are correct. Analyzing the abundances of all these elements in the sun, we can check if our analysis of the solar spectra is correct by studying meteorites. So meteorites is another way that we can know what is the composition of the sun. There are many different types of meteorites. They are listed here. And here on the y-axis, it's plotted for each element. Each element is a different color, divided magnesium, and relative to the sun, what are the components of all these different meteorites? The sun is, of course, at 1. And meteorites have very different components because they're made of different rocks. But there is a type of meteorites, the CI meteorite, that see they're almost like the sun. So people believe that these special meteorites, they are very primitive. They form very early. They captured the composition of the matter from which the sun formed, and then they kept it. They didn't get too much heat. They didn't get too much water. They didn't change their mineralogy, and so they are the same as the sun. And these are very rare type of meteorites. There's only 5 of them known. One of these is this famous Orgale that was observed fall in 1864. A few decades before that, people didn't even believe that meteorites actually came from the sky. They thought they were earth rock, but this was, again, one case where people could actually see the fall, and so it was confirmation. It's coming from out of the earth. And now people measure these 5 meteorites. They analyze what they are made of for all the elements that go into rock. Not the elements that don't go into rock, we cannot use meteorites. But for the elements that go into rocks, we can measure the meteorites, compare to what we see in the sun. Again, we normalize to magnesium, everything divided to this element. And you can see that if every point was on the line 1, everything would be perfectly the same. There are error bars, so we are within a 20% error bar between the sun and these meteorites. So we know quite well also what the sun is made of now. Not just the Earth, but the sun as well. So, okay, now we have the Earth, we have the sun. What about all the other stars? We don't have meteorites from other stars, unfortunately. We have the light from other stars, but again, it's coming from far away, and again, is a very complicated spectra to analyze. So the question is, what are the other stars made of? Are they the same as the sun, or are they different? And actually, I can already give away that the main result is that, yes, most stars are made of hydrogen and helium. So the discovery that was made 100 years ago also is the discovery that the universe is mostly made, the atomic part of the universe is mostly hydrogen and helium. But what about all the other elements? Would they be the same on other stars? Would they be different? Would there be carbon on a star far, far away so that life like us could happen or not? How do we know that? And actually, this also was a question that we didn't find out for quite a long time. In fact, until, say, the 1950s, people thought that they couldn't really see very many differences between the sun and the other stars. And so everybody thought that all the chemical elements, meaning from hydrogen to lead, uranium, thorium, all of them were made in the Big Bang. So the Big Bang, the first few minutes, everything is produced. The way we see it in the sun is the same in every galaxy, in every star, in every planet. Everywhere is the same, and nothing changed since then. So this picture was revolutionized, and again, it was a discovery that was a bit, that people were cautious about because no one expected this. So this is the, I would call the technetium big change. So technetium is a very special element because it wasn't discovered until 1937. And it was called the missing element. No one could find anywhere atoms with 43 electrons. They just didn't exist. And then in 1937, people discovered them in the radioactive residuals of some experiments that humans made. And so they called this atom technetium, which means artificial, because humans make it. It's not natural. We have to make it because it decays in less than 4 million years. So when it is made, then it stays there for 4 million years. But before we did these nuclear experiments, there was no technetium on the Earth, so no one could find it. So then something strange happened, because a few years later, Paul Merrill found the lines of technetium in the spectra of some giant stars. And this was really weird. So this is the original photographic plate. It's, in this case, black is where the photon hit, and white is where no photon was coming. And again, as function of the color of the photon. And you could see, everybody could see, there are clear white lines where the technetium would have captured the photon. People were very cautious because how is it possible that an element we don't have on Earth is found in a star? And putting together the fact that technetium decays in less than 4 million years, it's gone, and the fact that the stars that were observed, they were more than 4 million years old, this told us the first evidence that technetium was produced inside the stars. So technetium, as far as we know, is made by humans and stars. We do something the same as the stars. And now we know that, yes, this special type of giant stars, they make technetium, and they make a lot of other heavy elements, like tungsten and lead and barium and strontium, because they produce free neutrons. And these free neutrons, they can be captured by ion to produce very heavy elements. So now, this was in 1952. Since 1952, this has become a very important field of astrophysics. to discover more and more stars that, okay, they're mostly made of hydrogen and helium, but the other elements composition is not like the sun. They could have 1,000 more lead than the sun. They could have 100 more carbon than the sun. So they are different from each other. They are not all the same. And these are type of stars that I spent with my students and my group a lot of work studying, interpreting why they are so rich in these elements. So there are these giant stars with technetium. They are the one that produce it. They are giant stars at the end of their life. They're losing a lot of mass. This is a real picture of one of these stars. The star is actually in the middle there. All the material here is just winds. It's being blown out. Then when the star becomes very hot, it can illuminate the material around it. So we have this planetary nebula, beautiful picture that maybe some people have seen. And these planetary nebulae, some of them also have a lot more heavy elements than the sun. So because they come from the star that produced them. But then we found also a lot of stars that are not giant yet, but have a lot of heavy elements, so we explain them as binary interaction. So they were not the stars that made this element, but they had a companion who did and accreted the material. So now we observe them to be rich in these heavy elements. And in general, stars will all be like, there are some stars that are like the sun, we call them solar twins, they have same composition, but in generally speaking, are stars like the sun? Absolutely not. Again, we found the very big variability in the abundances of the elements in different stars, and this can be also studied. This is due to the fact that, as I mentioned, the stars make the element. When they die, they throw them out, and say you have a star somewhere in the galaxy will throw out a lot of lead, for example. And then new star will form from this material that was processed by stars, and the new star will have a different composition than the previous generation. And then they go again, they spend their life, they die. When they die again, they produce elements, and we go around and around in the galaxy. So a star will have a different composition according to when it's born and where it's born. And this is a big field of study that with my group we also worked on to try to understand the evolution of the galaxy, not just of stars, but how the galaxy evolves thanks to stars. Okay, now this was a bit of an introduction. Now I'm going to go a bit deeper because this is my favorite part. We're talking about the chemical elements. And this is carbon, which is 6 protons in the nucleus, 6 electrons, and 6 neutrons, which is not true because there's isotopes. Isotopes, what does it mean? It means that you have an element, so the number of electrons and the number of protons stay the same. For carbon, it's 6, there's no way to change that. But the number of neutrons can change. Carbon can have 7 neutrons, 8 neutrons, 9, 10, 11 neutrons. And these are called isotopes. So from now on, I'm not talking anymore about the atomic number, the electron and proton number. I'm going to talk about the mass of the isotope. And this is the proton number plus the neutron number. The electrons don't weigh very much, so I'm not counting them here. So from now on, I will talk about mass, the atomic mass, not the atomic number. So when we talk about isotopes, we add a dimension to the periodic table, basically. So the periodic table is when you change the proton number. But now we have a nuclide map where we also change the neutron number in this direction. For example, calcium 48 has mass 48 because it has 20 protons and 28 neutrons. Lead 208 has 82 protons and 126 neutrons, etc. And on this nuclei chart, the stable nuclei are the black boxes. Everything else decays one way or another. And actually now, this is the nuclei that we know well, but there's other nuclei that you can form out of this area here that are the current focus of a lot of research to try to understand the nuclei that are even higher up there, very, very heavy. So if we look, for example, at carbon, nitrogen, and oxygen, which are located down here, each of them have different isotopes. Maybe people sometimes don't realize that oxygen, okay, 99.7% is oxygen 16, but there's also 17 and 18. And carbon, in our body, 1/100 carbon atom is made of carbon 13. It has 7 neutrons. And there's another element I will talk a lot for the next part of the talk. I'm taking this as an example element because there's a lot of studies about it. Molybdenum. Molybdenum has 7 stable isotopes. So there is a huge variety, so much information we can get from molybdenum. And just above molybdenum, so molybdenum has 42 protons. Just above molybdenum, you see the technetium with 43 protons. There's no stable boxes there. So I wasn't lying. The technetium doesn't have any stable isotopes. They all decay. Okay, so I want to know the isotopic composition of the sun, the isotopic composition of stars, because this is much more information about the processes that make these nuclei. Can I do that? Can I observe isotopes in stars and in the sun? Not really. The problem is that isotopes behave the same from the atomic level. So the spectra of carbon doesn't change if there's a different isotope. It changes a tiny, tiny bit, and it's very difficult to see this in stellar spectra. We can observe it using molecules. For example, for the sun, we can see carbon isotopes, and in some stars that form molecules, we can see isotopic molecules that are made of different isotopes. But in general, it's very difficult. People try, and they do in some cases. So what did people do? They said, well, doesn't matter. Let's just take the Earth composition. It's going to be the same as the sun, as our body, as Jupiter. Anything will have the same isotopic composition because isotopes don't change. They don't care about chemistry. It doesn't matter if it's a cell in your body or a plasma blob in the sun. It will have the same isotopes or some rocks on Earth. And so people have done that, and they have derived the much more detailed abundances of the sun, because this time we are plotting them in terms of atomic mass. So each isotope, we know how much there is. So recapping, the elemental abundances are from solar spectra and meteorites. The isotopic fraction of each element are taken from the Earth. Assuming, as we think is correct, that more or less they will be the same everywhere. And this is giving us the real indication of how to make this kind of abundances in the universe, in the solar system, and in stars in general, because now we see the nuclear physics. When we have isotope, we can see the nuclear physics. And here, for example, the abundances are divided in atoms that have nuclei with the odd number of nucleons, proton plus neutrons, and those that have an odd number. And you see, the one with even number are more abundant. We know from nuclear physics that they are more stable. So this makes sense, because if they are more stable, once we produce them, they're harder to destroy. But what are all these peaks, and why there's this zigzagging? This again came from nuclear physics features. So let me explain. Let's take an oxygen atom. It had 8 electrons, 8 protons, and either 8, 9, or 10 neutrons. And if I imagine I add 2 electrons, in the outer shell. I can do that. I still have space for 2 electrons. And then I get a neon atom, which has 10 electrons, is a noble gas. This shell is full. The first one can only contain 2 electrons. The second one can only contain 10 electrons. This atom is happy as it is. It's a noble gas. It doesn't want to lose an electron. It doesn't want to capture it. It's full. It's satisfied as it is. This is for the atoms. But the nucleus does the same thing. So the nucleus, if we want, we can look at it in the same way as we see electrons in terms of a model of shells. Also, the protons and neutrons, they follow quantum physics law. They can only sit on energy levels that are very given. They're not everywhere in the nucleus moving around. They have special energy. And this means that the nucleus will behave in the same ways as an atom, as a noble gas, once its shell is full. And these numbers, they're not the same as the atom because the physics is different. The nuclear force is different from what happens in the atoms. And so the numbers are different. The magic number, they were called magic numbers because no one understood why this was the case, that this nuclei would be so stable. They are different from the noble gas number, and they apply to both protons and neutrons. So for the nuclear physics, we can have double magic, so double noble gas equivalent. For example, helium is very interesting because helium is 2 protons, 2 neutrons, so it's double magic nucleus, and is a noble gas because the first shell of the electron is full as well. It's a very special element. But also oxygen-16 is special because it has 2 protons and 2 neutrons. It's magic. Lead, 208. Why there's so much lead-208? Because it had 82 protons and 126 neutrons. It's double magic. And this was a Nobel Prize in 1963 explaining why the nucleus behave in this way. So if we go back to our picture, people in the 50s, they put together my field. That was the start of my field. You took astronomy and astrophysics, meteoritic and geochemistry, because you need the isotopic abundances, and nuclear physics. And then they could say, okay, now we think we know what are the nuclear processes inside stars, in some cases even inside which stars, but we're still working on exactly where all this happens. And they depend on nuclear features. For example, we have hydrogen, helium, another type of burning in stars that produces peaks at magic number less than 20. Actually, these are all multiplication of 4 because helium is so stable that it makes stable anything made of a number of helium atoms. And there's magic numbers here that of all the elements produced by neutron captures, because these elements, these isotopes are stable. They don't like to capture a neutron, so they're produced and then they rather accumulate. The ion peak is a different story. The ion peak comes from nickel 56, which is an unstable isotope, but it has the highest energy, the highest binding energy. So if we have a lot of reactions happening and material is going crazy, capturing and disintegrating, nickel 56 will be the one that disintegrates the less. And then it decays into ion 56, and so we have this peak here. Okay, now this was a little bit deeper introduction. Now I'm going to go in what it's for me one of the most exciting topics in the field, starting from the past 15 years. I was saying before that everything in the solar system will have the same isotopic composition. I was lying, partly lying. I will show you why. Because actually, this is not 100% true. So what happens is that isotopic variability is found in the solar system. We didn't expect that. People didn't expect that. I will show you why. And when we talk about isotopes, I'm talking about isotopic changes. Isotopes need stars to be changed because we have to do something in the nucleus. We have to have some nuclear reaction. Nuclear reaction can only happen at temperature million to billion of degrees. This didn't happen in the solar system. It didn't happen in the disk, it didn't happen when planet formed, nothing like that was reached. We need material from inside the star to be able to change the isotopic composition. So there was something stellar made that is still left the signature in the solar system. And why it took us a long time to discover it? Because these changes are tiny, they're very, very small. I will show you examples. So this is a figure that shows, starting from the 1960s, what is the number of elements for which we know we have observed isotopic variability. And in the 1970s, the digital teams thought this is mass spectrometry instrument. You want an isotope, you want to measure the mass. You get a sample, you get some ions out, and you want to measure what is the mass coming out, so how many ions of mass or different mass are coming out. And this was the first important development in this type of thermal ionization mass spectrometry that allowed people in the 70s to start noticing that there's some material inside meteorites. And it's this material here, this white, a bit longish inclusion. They are from millimeter to centimeter big. And they already saw that there was a lot of isotopic variability there. But these are special matter. They are the first solids that formed in the solar system. They are the oldest solid we found that form in the solar system. They are the reason why we know the age of the sun is 4.567 billion years. So people thought, okay, these are a bit special thing. They collected some heterogeneity. Not everything was very well mixed at the very beginning. But then this other MC-ICP-MS type of mass spectrometry appeared in about like 20 years ago. And since then, people start seeing variability not only in the little special material, but in the bulk rock, meaning the average of the meteorite is different from the average of another meteorite. So this is what is average composition. And we started in the year 2000 with 5 elements, and now we have 23. So it is not a special thing. It seems it's happening. It's quite widespread, this variability. And then it took, like only in the past 10 years, people have started to analyze other bits and pieces of meteorite. These are also smaller, they're more difficult, but they're seeing variability also there. So what do we think is happening? Okay, first I will show you one example of what people measure, so you can get the feeling of why it's so difficult. This is molybdenum. I use molybdenum for the rest of the talk as an example. It has 7 stable isotopes, and in this figure, this is the Earth molybdenum isotopic composition using 4 different isotopes. And this is a paper from this year. These are the Earth samples here that they measure in this recent paper, and these are some estimates. The estimate of the molybdenum composition of the Earth, there was a paper in 2001, was here. The new one is here. What am I talking about? This unit, called mu, means that -10, so this sample here, is 0.0001% less than laboratory standard. So people are measuring variation on the 6 or 7 significant digits. This is why it was so complicated to find them. And actually, I don't want to confuse too much, but this is the actual formula of the mu unit that is plotted here. So we have the sample composition, the laboratory standard, you always need that when you do an experiment, but then people have to do this internal normalization using another isotope with an exponential formula that depends on the mass, because there is mass-dependent fractionation that happened during the experiment, and this has to be removed. It's not the real composition, it's an artificial effect. This is just to show that this is not easy. And then people multiply the number they get by 1 million, because otherwise we'll have to make a plot that says 0.0000000 something, and that's a bit annoying, right? So here we have from minus 30 to 20. Now, you might start to wonder, who cares? Why are people spending all this money, buying all this instrument, working for 2 years to get this sample that are 000 something different? Why do we care about this? Well, this is what can tell us how the Earth formed. That's why people are fighting on this. I will zoom out this picture. If we zoom out, this is the same that I showed before. But we also have the same analysis for meteorites. These are meteorites from the inner solar system, and now we are moving now to 120 mu, so it's only 0.0001 different. And this is the outer solar system. Meteorites from the outer solar system are located above this arrow, but on this blue line. So if the Earth is here, you need some material from the outer solar system to make the Earth. It's not on the red line. If the Earth is here, you don't need material from the outer solar system. So this is a completely quite different scenario for the formation of rocky planets. Material from the outer solar system would come in form of pebbles, small rocks. But if we only need material from the inner solar system, we can form the Earth from planetesimals that are already, say, kilometers in size. And this is, we don't know what's the answer. We don't know how the Earth formed. We don't know how other rocky planets in the galaxy form. This is why people are spending a lot of time trying to work out these tiny variations. From the astrophysics point of view, why am I interested? I'm not a planetary scientist. I find this fascinating, but I cannot really contribute with any planet formation scenarios or anything. But what I can do is to look at this structure of this data and say, well, what was the stellar material that made this kind of structure in the molybdenum in the solar system? And this is why I am interested, because these are very small variations, but they're not random. They are on some lines. And so they have an origin that is a structured origin from nuclear reaction that happen in some stars. And this is what I want to understand. So what is the picture? What do we think at the moment that how this happened? So we have our stars. These are my giant stars, the same one that make technetium, the ones that make neutrons so that we can make heavy elements like molybdenum, palladium, cadmium, etc. They have a lot of winds, if you remember that picture. They are throwing out material. In the winds, they also make a lot of dust. They are observed to be very dusty. And this gas and dust is expelled into the medium around the stars. We also have supernovae. Supernovae also can make a lot of dust. So we have little stardust bits that are coming out of supernova ejecta. And then this dust is hanging around in the interstellar medium. In the interstellar medium also we can make solids. For example, there can be mantles that are formed on top of the stardust. They will not have the composition of the stardust because they didn't form in stars. They will have the composition of the interstellar medium that was already all mixed up, an average of thousands of stars, so they have a different isotopic composition. Then the solar system forms. What happens? This dust ends up in the disk. And what can happen? It can be separated, for example, by dust processing, thermal processing. Closer to the sun is hotter, farther from the sun is colder. Near to the sun, there will be some type of solids that are destroyed. They are vaporized, so they disappear from close to the sun. But outer there, they remain. So the relative abundance of the stardust and other type of dust can change along the disk. This could be also due to the size of mineralogy. There's another possibility, and people think both of these happened, is that while the sun was forming, it was accreting material that was changing the isotopic composition. Just a tiny bit. As I show you, the variations are not big, but something changed, so the material from which the sun accreted was not homogeneous to start with. So basically, in this case, we inherit some variability. In this other process, we make it in the disk. And then I show you again this figure. This is a very important discovery, that the outer solar system is here, the inner solar system is here, there is a gap. We haven't found anything in between, really. It seems to be well separated. How could have happened? People have proposed a barrier to block material from mixing. And so we have two very different separated type of matter in the outer and the inner solar system. The formation of Jupiter, if it happened very fast, the Jupiter core, if it happened in less than 1 million years, then this could be a good explanation. And now I wonder if anyone's thinking, okay, nice, that's a nice fairy tale, speculations, sounds good, but are you inventing all these? Are people just making things up as they go, just inventing stories? Well, no, because we have some evidence of at least a part of it that happened. And the evidence comes from the fact that these dust grains here, we have them, we found them. We found stardust grains inside meteorites. So we found very tiny, so everything is tiny, but this is a 1 micrometer scale. This is a grain that's about 10 micrometers, so it's 1/1000th of a millimeter. It's really dust. But people found them in meteorites since the 80s. In the 80s, people started to manage to extract them. There's different type of them, silicon carbide, graphite, rubin, and sapphire. They're usually gems because they had to survive all the way from their star to the solar system and the meteorite. And this is a very exciting topic for me that, in fact, I started working on it when I was master's student, and I still work on this, try to understand what is the makeup of this dust, which stars do they come from, and what do they tell us about the nuclear reaction in these stars. So we have the stardust that at least some part of the story must be true, because there was some stardust. There is not much of it, but maybe was enough. In some cases it could have been. And so let's look at this and put everything together. This is stardust data for molybdenum. I'm going again to the example of molybdenum because I want them to put them together. In this figure, each data point is a different stardust. People can measure the isotope of stardust because it's a sample. We have it in the laboratory. We can put it in a mass spectrometer. So people have done that since the 80s, and this is some collection of stardust from many studies. I want to point out that now I am using a different unit. It's not the unit I was using before. Now people use a delta. Delta means that we have an isotopic ratio, for example, 94 molybdenum, 96, and it's calculated the variation relative to the laboratory standard multiplied by 1,000. It's like a percent, but with a more zero. So for example, this grain is minus 400 in delta. It means it's minus 40% less than the standard. What I was showing you before, mu is by 1,000,000. So mu is 10 to the 6. Delta is 10 to the 3. So 100 mu is 0.1 delta. So the figure I showed you before is this little dot that you cannot see. I put the dot there, but it would be in 0.1 delta, and here the scale is 100. So the figure of the meteorites before and the Earth, you cannot see it on this plot. The stardust is really, really anomalous. It shows huge variation. And so the red line here is the best fit to this type of stardust that show the signature of neutron captures. The neutron capture that make the technetium in the giant stars that make the stardust, they also show molybdenum variation. Of course, molybdenum will capture neutrons and it will change its isotopic composition. So now what people have done, what you can do is take those red lines and convert them into the mu, into the other unit. So we go back to the previous plot, and if we put the stardust on this plot, we get this line, which is very similar in the slope to what's happening in the inner and the outer solar system. There's two important things that I finish with. One is, where is the Earth? The Earth is here or here. Anyway, it's here. The Earth is the solar system material with the most abundant stardust from giant stars that we ever found. So this is a bit strange, maybe. Why should the Earth be the most abundant? So we see from the outer solar system to the inner solar system, we are moving to more stardust. But why is the Earth the most abundant? The Earth should have formed from something around here, or maybe coming from out, we don't know. But it should be a mixture of something. So there should be material that is even more rich in stardust, and we never found it. In the meteoritic inventory, there's no meteorites that have more strong signature than the Earth. So this is another big problem. Maybe the material fell on the sun, so we'll never find it. Would be good to know Mercury and Venus molybdenum composition. So people predict it should be even more rich, it should have even a stronger signature, but we don't have a piece of Mercury or a piece of Venus. That's a problem. So at the moment we cannot answer. Other people are finding completely different scenarios to explain this. They explain molybdenum as something that happens during pebble accretion, during the planetary formation of the Earth. So it's something that happened later. So this is very highly debated. And the other point that I want to finish is these two lines. There's one line here, one line is the stardust, and one line is the outer solar system. Are they parallel or not? Again, you might think, well, who cares, more or less. No, people are spending a lot of time trying to find out the exact slope of these lines. And we're not sure. This is different studies. This is the stardust. It's a bit different, depending on different studies. We have to be careful. The outer solar system seems to be here. The inner solar system, this is the latest study, we don't know. But this slope is completely controlled in the stardust material by the neutron captures. So I wanted to know, what do the neutron capture predict? Can we tell something about the type of stardust that produce the different slopes, the type of stars? And my problem at the moment is that the nuclear physics input in the models is not very robust. For example, it depends a lot on the neutron capture, or the probability of molybdenum-95 to capture a neutron. And if I use older values, I get this slope, which is never good. A newer value is better, at least for some of these. I still have variations because different masses, different stars of different masses, they would still move the slope. But this is still a bit open. And in fact, this is the motivation for nuclear physics experiments. So people at CERN, at the Enthoff experiment, as well as in Belgium, they understood how important all this is, and they measured all the neutron capture cross-section of the molybdenum isotopes. And now they are analyzing all the data, and this is my future work that I am excited about. Hopefully they come out with something very accurate and very precise, because then I can take this input, I can put it in my stellar models, and I can derive the signature of the neutron capture in different type of giant stars. Then I can identify which type of giant star would have produced which slope exactly. And that depends also which kind of stardust they would have made. Would it be silicon carbide or oxygen-rich stardust, for example, big or small? And then if the two inner and outer solar system behave differently, I can tell which star that it was that made the difference and from which star it came. And so this is going into the future. I don't have results yet, but hopefully in the next few years. And this is the example of molybdenum. I want to finish with this because it's the classic, so I have to put this in. Everyone's heard. We are stardust, we are made of stars, so it's here. Is it true or not? I've been saying a bit of true, a bit of lies, but now, yes. Our body is 65% supernova material, because oxygen is from supernova, 20% from giant stars, carbon and nitrogen. So again, that was not that correct, because we are 10% hydrogen. So I'm 50 kilos, 5 kilos of someone who weighed 50 kilos is from the Big Bang. So actually 10% of us was around from the beginning of the universe 13 billion years ago. Moreover, this sentence I don't like completely because oxygen, carbon, hydrogen, and nitrogen are gas. Some of them, a little bit goes in dust, and in fact, of course, silicon oxide and sand is made of that, but 2/3 of oxygen, it goes with carbon, make carbon monoxide. It's gas, it's not dust. So I would like to change that sentence to say that we are made of stellar and Big Bang gas. This is a bit more precise to get to the end so that everybody can now know. I find fascinating that there's also Big Bang material that is part of us that was not modified by anything. I want to finish with my acknowledgements. My mentors, Professor Gallino, Keppeler, and Zinner. So he was my master thesis supervisor and really taught me everything about stellar nucleosynthesis, everything I know. Franz Keppeler was a nuclear physicist who also studied nucleosynthesis a lot and did a lot of pioneering experiments, especially about neutron capture. And Ernst Zinner was one of the discoverers of stardust. He was actually listed as for the Nobel Prize a few times for his discoveries. And I want to mention them especially because it's not just they were my mentors in terms of what they taught me scientifically, but personally they were extremely supportive, especially when I was a young student and you feel very unsure about yourself. And they with their personality, they really made my life completely different from what it could have been. Also, I want to thank the director of the observatory, the 3 directors since the time I moved here, because also from them I always had so much support. You had to be here. Thank you for all the help in the past 11 years. Okay, so this is for the past 11 years. Most of my co-workers and I think all the postdocs and all the students are in this picture, and it is thanks to them that I can still do in science, because there's so much, of course, management and things to do, but thanks to all the young people that we can still push all these exciting new topics. And I also thanks the people who helped me translating the slides. Every mistake that's left there is completely my fault, I just want to say, but thank you for all the help. And I want to finish to thank my family, of course, my mom and my brothers, and especially my children and my husband, because they had to move countries many times. They had to learn languages just for sake of following me, being able to keep on doing science. So they've been very brave, especially all the very young children having to change their life so many times. So that's a very big thank for their support. And of course, thank you for the attention. Thank you for being here and listening to the whole presentation. Thank you.
Thank you, Maria. Nagyon szépen köszönjük ezt a tényleg érdekes és nagyon nagyívű előadást, úgyhogy akkor egy dolog maradt hátra, hogy akkor most már tényleg abszolút hivatalosan is Magyar Tudományos Akadémia fizikai tudományok osztályának levelező tagjává avassunk. Így átadom az oklevelet, és gratulálok.